Company overview. TerramEarth manufactures heavy equipment for the mining and agricultural industries. About 80% of their business is from mining and 20% from agriculture. They currently have over 500 dealers and service centers in 100 countries. Their mission is to build products that make their customers more productive. Company background. TerramEarth formed in 1946, when several small, family-owned companies combined to retool after World War II. The company cares about their employees and customers and considers them to be extended members of their family. TerramEarth is proud of their ability to innovate on their core products and find new markets as their customers' needs change. For the past 20 years, trends in the industry have been largely toward increasing productivity by using larger vehicles with a human operator. Solution concept. There are 20 million TerramEarth vehicles in operation that collect 120 fields of data per second. Data is stored locally on the vehicle and can be accessed for analysis when a vehicle is serviced. The data is downloaded via a maintenance port. This same port can be used to adjust operational parameters, allowing the vehicles to be upgraded in the field with new computing modules. Approximately 200,000 vehicles are connected to a cellular network, allowing TerramEarth to collect data directly. At a rate of 120 fields of data per second, with 22 hours of operation per day. TerramEarth collects a total of about 9 terabytes per day from these connected vehicles. Existing technical environment. TerramEarth's existing architecture is composed of Linux-based systems that reside in a data center. These systems gzip CSV files from the field and upload via FTP, transform and aggregate them, and place the data in their data warehouse. Because this process takes time, aggregated reports are based on data that is 3 weeks old. With this data, TerramEarth has been able to preemptively stock replacement parts and reduce unplanned downtime of their vehicles by 60%. However, because the data is stale, some customers are without their vehicles for up to 4 weeks while they wait for replacement parts. Business requirements. Decrease unplanned vehicle downtime to less than 1 week, without increasing the cost of carrying surplus inventory. Support the dealer network with more data on how their customers use their equipment. IP better position new products and services. Have the ability to partner with different companies, especially with seed and fertilizer suppliers in the fast-growing agricultural business, to create compelling joint offerings for their customers. CEO statement. We have been successful in capitalizing on the trend toward larger vehicles to increase the productivity of our customers. Technological change is occurring rapidly, and TerramEarth has taken advantage of connected devices technology to provide our customers with better services, such as our intelligent farming equipment. With this technology, we have been able to increase farmers' yields by 25% by using past trends to adjust how our vehicles operate. These advances have led to the rapid growth of our agricultural product line, which we expect will generate 50% of our revenues by 2020. CTO statement. Our competitive advantage has always been in the manufacturing process, with our ability to build better vehicles for lower cost than our competitors. However, new products with different approaches are constantly being developed, and I'm concerned that we lack the skills to undergo the next wave of transformations in our industry. Unfortunately, our CEO doesn't take technology obsolescence seriously, and he considers the many new companies in our industry to be niche players. My goals are to build our skills while addressing immediate market needs through incremental innovations. Question 159. For this question, refer to the TerramEarth case study. TerramEarth's CTO wants to use the raw data from connected vehicles to help identify approximately when a vehicle in the development team will experience a component failure. You want to allow analysts to centrally query the vehicle data. Which architecture should you recommend? IoT device - Google Cloud Load Balancing - Google Kubernetes Engine - Cloud Pub / Sub - Cloud Dataflow - BigQuery - Analysis. B. IoT device - App Engine, Flexible Environment - Cloud Pub / Sub - Cloud Dataflow - BigQuery - Analysis. Okay, this question is based on the TerramEarth case study. The main goal is to replace their old, slow, FTP-based data pipeline with a modern, scalable, real-time analytics platform on Google Cloud. We need to choose the best architecture to do this. Both proposed architectures use the same core components for the real-time pipeline. Cloud Pub / Sub for ingesting the data stream, Cloud Dataflow for processing it, and BigQuery for storing and analyzing it. This is the standard Google recommended pattern. The only difference between the two options is the very first step, the ingestion layer that receives the FTP data from the vehicles. Option B suggests using the App Engine flexible environment. This is not the best choice. App Engine is a platform that is highly optimized for standard web applications using protocols like HTTP. While it can run custom containers, setting up a high-volume FTP server on it is less straightforward and offers less networking flexibility than the alternative. This brings us to option A, which is the correct and more robust solution. It suggests using a combination of a Google Cloud Load Balancer and Google Kubernetes Engine, or GKE, for the ingestion layer. This is a much better fit for handling a custom protocol like FTP from hundreds of thousands of devices. GKE provides the flexibility and scalability needed to run the custom FTP server containers, and the load balancer efficiently distributes the massive number of incoming connections. This data is then fed into the standard pub/sub, Dataflow, and BigQuery pipeline for processing and analysis. Therefore, the recommended architecture is a IoT device - Google Cloud Load Balancing - Google Kubernetes Engine - Cloud Pub/Sub - Cloud Dataflow - BigQuery - Analysis. Question 160. For this question, refer to the TerramEarth case study. The TerramEarth development team wants to create an API to meet the company's business requirements. You want the development team to focus their development effort on business value versus creating a custom framework. Which method should they use? Use Google App Engine with Google Cloud Endpoints. Focus on an API for dealers and partners. B. Use Google App Engine with a JXRS Jersey Java-based framework. Focus on an API for the public. C. Use Google App Engine with the Swagger Open API Specification Framework. Focus on an API for the public. D. Use Google Container Engine with a Django Python container. Focus on an API for the public. E. Use Google Container Engine with a Tomcat container with the Swagger Open API Specification Framework. Focus on an API for dealers and partners. Okay, this question is based on the TerramEarth case study and asks us to choose the best technology stack for building a new API. The two most important requirements are that the solution should have minimal operational overhead so the team can focus on business logic, and it must serve the correct audience mentioned in the case study. With that in mind, let's first identify the correct audience. The case study states the API is to support the dealer network and to partner with different companies. Therefore, any option that suggests focusing on an API for the public, like options B, C, and D, is incorrect. This leaves us with options A and E. The difference between them is the platform. App Engine versus Google Kubernetes Engine. The question requires a solution that allows the team to focus on business value instead of building a custom framework or managing infrastructure. Google Kubernetes Engine, or GKE, is a powerful container orchestrator, but it requires more operational management than App Engine. App Engine is a fully managed, serverless platform where Google handles the infrastructure for you. Therefore, App Engine is the better choice for minimizing operational overhead. Let's look closer at option A. It combines the right platform, App Engine, with the right API tool, Google Cloud Endpoints. Cloud Endpoints is a managed API gateway that provides many features like authentication and monitoring out of the box, which further reduces the amount of custom framework development needed. It also correctly identifies the target audience as dealers and partners. Therefore, the method that best meets all the requirements is a use Google App Engine with Google Cloud Endpoints and focus on an API for dealers and partners. Question 161. For this question, refer to the TerramEarth case study. Your development team has created a structured API to retrieve vehicle data. They want to allow third parties to develop tools for dealerships that use this vehicle event data. You want to support delegated authorization against this data. What should you do? A. Build or leverage an OAuth-compatible access control system. B. Build SAML 2.0 SSO compatibility into your authentication system. C. Restrict data access based on the source IP address of the partner systems. D. Create secondary credentials for each dealer that can be given to the trusted third party. Okay, this is a security question from the TerramEarth case study. The most important phrase here is delegated authorization. This means we need a system that allows a user, in this case a dealership, to grant a third-party application limited access to their data without having to share their password. With that in mind, let's look at our options. Let's start with option B, which suggests using SAML. This is incorrect. SAML is a standard for authentication and single sign-on, which is about verifying a user's identity. It is not the right tool for authorizing a third-party application to act on a user's behalf. Next, option C, restricting access by IP address. This is a weak and inflexible security measure. It can't distinguish between different users from the same network and doesn't provide the granular, revocable permissions needed for this scenario. Option D suggests creating secondary credentials for the third party to use. This is a very bad security practice. Sharing credentials of any kind is risky, difficult to manage, and makes it hard for the user to revoke access. This brings us to option A, which is the correct and industry-standard solution. OAuth 2.0 is the protocol specifically designed for delegated authorization. It's the same technology that allows you to click Log in with Google on a third-party website. It allows the dealer to grant the third-party application specific, limited permissions to their data for a limited time, without ever sharing their actual username and password. The dealer can also revoke this access at any time. Therefore, the correct thing to do is build or leverage an OAuth-compatible access control system. Question 162. For this question, refer to the TerramEarth case study. TerramEarth plans to connect all 20 million vehicles in the field to the cloud. This increases the volume to 20,600,000 byte records a second for 40 terabytes an hour. How should you design the data ingestion? Vehicles write data directly to GCS. B. Vehicles write data directly to Google Cloud Pub/Sub. C. Vehicles stream data directly to Google BigQuery. D. Vehicles continue to write data using the existing system, FTP. Okay, this is a big data architecture question from the TerramEarth case study. The challenge here is to design a data ingestion system that can handle an absolutely massive amount of data, 20 million records every single second. We need a service that is built for global scale and extreme throughput. With that in mind, let's look at our options. Let's start with option D, which suggests continuing to use the existing FTP system. This is incorrect because the case study makes it clear that the current FTP system is the core problem. It's slow, not scalable, and the reason they need a new solution. Next, let's look at option A, writing directly to Google Cloud Storage. This is also not a good fit. Cloud storage is an object store, which is optimized for large files, not for millions of tiny, individual records being written every second. It would not be performant for this kind of workload. Option C suggests streaming data directly to BigQuery. While BigQuery does have a streaming API, using it as the front door for 20 million writes per second is not its intended purpose and would be very costly. The recommended practice is to use a dedicated ingestion service in front of BigQuery. This brings us to option B, which is the correct and recommended solution. Cloud Pub/Sub is a fully managed, global messaging service designed for exactly this scenario. It's built to ingest millions of events per second from devices all over the world. It acts as a highly scalable and reliable buffer, safely capturing all the incoming data and decoupling the vehicles from the back-end data processing systems. This is the perfect front door for a high-volume IoT data pipeline. Therefore, the way you should design the data ingestion is B. Vehicles write data directly to Google Cloud Pub/Sub. Question 163. For this question, refer to the TerramEarth case study. You analyzed TerramEarth's business requirement to reduce downtime and found that they can achieve a majority of time saving by reducing customers' wait time for parts. You decided to focus on reduction of the 3 weeks aggregate reporting time. Which modifications to the company's processes should you recommend? A. Migrate from CSV to binary format, migrate from FTP to SFTP transport, and develop machine learning analysis of metrics. B. Migrate from FTP to streaming transport, migrate from CSV to binary format, and develop machine learning analysis of metrics. C. Increase fleet cellular connectivity to 80%, migrate from FTP to streaming transport, and develop machine learning analysis of metrics. D. Migrate from FTP to SFTP transport, develop machine learning analysis of metrics, and increase dealer local inventory by a fixed factor. Okay, this question is based on the TerramEarth case study. The central problem we need to solve is the massive 3-week delay in their data reporting, which is preventing them from predicting vehicle failures. We need a comprehensive solution that addresses the root causes of this delay. With that in mind, let's evaluate our options. Let's start with options A and D, which both suggest switching from FTP to SFTP. This is incorrect. SFTP is just a secure version of FTP. It's still a slow, batch-based file transfer protocol. This change would do nothing to reduce the 3-week delay. Option D also incorrectly suggests increasing dealer inventory, which the case study states they want to avoid. Next, let's look at option B. It correctly suggests migrating to a modern streaming transport, which is a good technical step. However, this alone is not enough. The case study mentions that only a tiny fraction of their vehicles have the cellular connectivity needed to stream data. A real-time pipeline is useless if you don't have real-time data to put into it. This brings us to option C, which is the correct and most complete solution. It tackles the problem from all angles. First, and most importantly, it addresses the core data problem by increasing fleet cellular connectivity. This is the strategic change needed to get the real-time data required. Second, it implements the necessary technology change by migrating from FTP to streaming transport to handle this new data flow. Finally, with the new real-time data pipeline in place, they can develop machine learning analysis to predict failures, which was their ultimate business goal. Therefore, the set of modifications that would solve their problem is C. Increase fleet cellular connectivity to 80%, migrate from FTP to streaming transport, and develop machine learning analysis of metrics. Question 164. For this question, refer to the TerramEarth case study. Which of TerramEarth's legacy enterprise processes will experience significant change as a result of increased Google Cloud Platform adoption? OpEx/CapEx allocation, land changes, capacity planning. B. Capacity planning, TCO calculations, OpEx/CapEx allocation. C. Capacity planning, utilization measurement, data center expansion. D. Data center expansion, TCO calculations, utilization measurement. Okay, this question from the TerramEarth case study is about the business and financial impact of moving from a traditional on-premises data center to Google Cloud. We need to identify which core enterprise processes are most significantly changed by this shift. With that in mind, let's evaluate our options. Let's first look at the options that include data center expansion, which are C and D. These are incorrect because moving to the cloud doesn't just change the process of data center expansion, it effectively eliminates it. You no longer need to plan for and build out physical space. Next, let's look at option A. It mentions land changes. While you will need to manage the connection to the cloud, the day-to-day management of your local office network isn't one of the most fundamentally changed processes compared to the major shifts in financial and capacity planning. This brings us to option B, which is the correct answer. This option lists the 3 processes that are most profoundly transformed by adopting the cloud. Capacity planning changes from a long-term guessing game of buying hardware to an on-demand, elastic model. TCO calculations, or how you measure the total cost of ownership, are completely different when you're paying for services instead of physical assets, power, and cooling. Finally, OpEx/CapEx allocation represents the fundamental financial shift from capital expenditures, which is buying hardware, to operating expenditures, which is paying a recurring service bill. Therefore, the processes that will experience the most significant change are B. Capacity planning, TCO calculations, and OpEx/CapEx allocation. Question 165. For this question, refer to the TerramEarth case study. To speed up data retrieval, more vehicles will be upgraded to cellular connections and be able to transmit data to the ETL process. The current FTP process is error-prone and restarts the data transfer from the start of the file when connections fail, which happens often. You want to improve the reliability of the solution and minimize data transfer time on the cellular connections. What should you do? A. Use one Google Container Engine cluster of FTP servers. Save the data to a multi-regional bucket. Run the ETL process using data in the bucket. B. Use multiple Google Container Engine clusters running FTP servers located in different regions. Save the data to multi-regional buckets in US, EU, and Asia. Run the ETL process using the data in the bucket. C. Directly transfer the files to different Google Cloud multi-regional storage bucket locations in US, EU, and Asia using Google APIs over HTTPS. Run the ETL process using the data in the bucket. D. Directly transfer the files to a different Google Cloud regional storage bucket location in US, EU, and Asia using Google APIs over HTTPS. Run the ETL process to retrieve the data from each regional bucket. Okay, this question from the TerramEarth case study is about fixing their data transfer process. We need a solution that is more reliable than their current error-prone FTP system and also minimizes the data transfer time for vehicles connecting over cellular networks around the world. With that in mind, let's evaluate our options. Let's start by looking at options A and B. Both of these are incorrect because they continue to rely on the FTP protocol, which is the core of the problem. FTP is not inherently reliable for flaky connections, as it often has to restart transfers from the beginning when a connection fails. Next, let's look at option C. This option correctly suggests using the Google APIs over HTTP, which is a good step. However, it recommends using multi-regional buckets. This is not the best choice for minimizing transfer time. If a vehicle in Asia uploads to a US multi-region bucket, its data might have to travel across the ocean, which increases latency. This brings us to option D, which is the correct and most efficient solution. It solves both problems perfectly. To improve reliability, it uses the Google APIs over HTTP. These APIs support resumable uploads, which means if a cellular connection drops, the transfer can pick up where it left off instead of starting over. To minimize transfer time, it uses regional storage buckets in each continent. This allows a vehicle in Europe to upload to a European bucket and a vehicle in Asia to upload to an Asian bucket. Uploading to the nearest geographical location is the best way to reduce network latency and speed up transfers. Therefore, the best thing to do is D. Directly transfer the files to a different Google Cloud regional storage bucket location in US, EU, and Asia using Google APIs over HTTPS. Run the ETL process to retrieve the data from each regional bucket. Question 166. For this question, refer to the TerramEarth case study. TerramEarth's 20 million vehicles are scattered around the world. Based on the vehicle's location, its telemetry data is stored in a Google Cloud Storage, GCS, regional bucket, US, Europe, or Asia. The CTO has asked you to run a report on the raw telemetry data to determine why vehicles are breaking down after 100k miles. You want to run this job on all the data. What is the most cost-effective way to run this job? Move all the data into one zone, then launch a Cloud Dataproc cluster to run the job. B. Move all the data into one region, then launch a Google Cloud Dataproc cluster to run the job. C. Launch a cluster in each region to preprocess and compress the raw data. Then move the data into a multi-region bucket and use a Dataproc cluster to finish the job. D. Launch a cluster in each region to preprocess and compress the raw data. Then move the data into a region bucket and use a Cloud Dataproc cluster to finish the job. Okay, this is a big data architecture question from the TerramEarth case study. The most important requirement is to find the most cost-effective way to run a job on data that is spread all over the world. In Google Cloud, the biggest cost to watch out for in a scenario like this is network egress, which is the fee for moving data between regions. The best practice to minimize this cost is to bring your compute to your data. This means you should process the data as much as possible in the region where it already lives, to reduce its size before you move it anywhere else. With that principle in mind, let's look at our options. Let's look at options A and B. Both suggest moving all of the raw data into a single zone or region before processing it. This would be incredibly expensive, as you would have to pay the high network egress fees to move terabytes of raw data across continents. Next, let's look at option C. It correctly starts by pre-processing the data in each region. However, it then suggests moving the results to a multi-regional bucket. This isn't the most cost-effective choice because multi-regional buckets have higher storage costs than standard regional buckets. This brings us to option D, which is the correct and most cost-effective solution. This approach follows the bring compute to the data principle perfectly. You first launch a small dataproc cluster in each region to pre-process and compress the raw data locally. This significantly reduces the amount of data that needs to be moved. Then, you only transfer this much smaller processed data to a single regional bucket for the final analysis. This method drastically reduces your network egress costs, making it the most cost-effective design. Therefore, the best way to run this job is D. Launch a cluster in each region to pre-process and compress the raw data. Then move the data into a region bucket and use a cloud dataproc cluster to finish the job. Question 167. For this question, refer to the TerramEarth case study. TerramEarth has equipped unconnected trucks with servers and sensors to collect telemetry data. Next year, they want to use the data to train machine learning models. They want to store this data in the cloud while reducing costs. What should they do? Have the vehicle's computer compress the data in hourly snapshots and store it in a Google Cloud Storage (GCS) nearline bucket. B. Push the telemetry data in real time to a streaming dataflow job that compresses the data and store it in Google BigQuery. C. Push the telemetry data in real time to a streaming dataflow job that compresses the data and store it in Cloud Bigtable. D. Have the vehicle's computer compress the data in hourly snapshots and store it in a GCS cold line bucket. Okay, this question from the TerramEarth case study is about choosing the right data collection and storage strategy. The two most important clues in the question are that the trucks are unconnected and the data will only be used for training next year, with a goal of reducing costs. With that in mind, let's evaluate our options. Let's start with options B and C. Both of these are incorrect because they suggest pushing the data in real time. The question clearly states that the trucks are unconnected, so a real-time streaming solution is not possible. Now let's compare options A and D. Both correctly suggest a reasonable collection method for an offline vehicle, compressing data into hourly snapshots which can then be uploaded later. The only difference between them is the cloud storage class they recommend, nearline versus cold line. Option A suggests using a nearline bucket. Nearline is designed for data that you access infrequently, typically less than once a month. However, the requirement is to use the data next year, which means the access frequency is even lower. This brings us to option D, which is the correct and most cost-effective answer. It suggests using a cold line bucket. Cold line storage is specifically designed for long-term archival data that you expect to access less than once a year. Since the data will be stored until next year, cold line offers the lowest storage cost, perfectly matching the requirement to reduce costs. Therefore, the best thing to do is D. Have the vehicle's computer compress the data in hourly snapshots and store it in a GCS cold line bucket. Question 168. For this question, refer to the TerramEarth case study. Operational parameters such as oil pressure are adjustable on each of TerramEarth's vehicles to increase their efficiency, depending on their environmental conditions. Your primary goal is to increase the operating efficiency of all 20 million cellular and unconnected vehicles in the field. How can you accomplish this goal? A. Have your engineers inspect the data for patterns, and then create an algorithm with rules that make operational adjustments automatically. B. Capture all operating data, train machine learning models that identify ideal operations, and run locally to make operational adjustments automatically. C. Implement a Google Cloud Dataflow streaming job with a sliding window, and use Google Cloud Messaging (GCM) to make operational adjustments automatically. D. Capture all operating data, train machine learning models that identify ideal operations, and host in Google Cloud Machine Learning (ML) platform to make operational adjustments automatically. Okay, this is a machine learning architecture question from the TerramEarth case study. The most important constraint to pay attention to is that the solution must work for the entire fleet of 20 million vehicles, which includes both connected and, crucially, unconnected vehicles. With that in mind, let's look at our options. Let's first look at the options that require a continuous internet connection, which are C and D. Option C uses a streaming data flow job, and Option D hosts the machine learning model in the cloud for predictions. Both of these would require the vehicles to be constantly connected to the internet to send data and receive instructions. This means they would not work for the unconnected part of the fleet, so they are incorrect. Next, let's look at Option A, which suggests having engineers manually create a rule-based algorithm. This is also incorrect. With 20 million vehicles operating in countless different environments, it would be impossible for humans to manually discover all the complex patterns needed for optimization. This is a problem that requires machine learning. This brings us to Option B, which is the correct and most scalable solution. This describes a common and powerful pattern for IoT and edge computing. You first capture all the data from your entire fleet and use it to train a sophisticated machine learning model in the cloud. Then, you deploy that trained model to run locally on each vehicle's onboard computer. The model can then make real-time operational adjustments using the vehicle's own sensors, without needing to be connected to the internet. This solution works for both connected and unconnected vehicles, as the unconnected ones can receive model updates during their maintenance stops. Therefore, the way you can accomplish this goal is B. Capture all operating data, train machine learning models that identify ideal operations, and run them locally to make operational adjustments automatically. Question 169. Securing TerramEarth's autonomous vehicles. For this question, refer to the TerramEarth case study. Your agricultural division is experimenting with fully autonomous vehicles. You want your architecture to promote strong security during vehicle operation. Which two architectures should you consider? Choose two answers. Treat every microservice call between modules on the vehicle as untrusted. B. Require IPv6 for connectivity to ensure a secure address space. C. Use a trusted platform module, TPM, and verify firmware and binaries on boot. D. Use a functional programming language to isolate code execution cycles. E. Use multiple connectivity subsystems for redundancy. F. Enclose the vehicle's drive electronics in a Faraday cage to isolate chips. Okay, this question from the TerramEarth case study is about designing a secure architecture for a complex system like an autonomous vehicle. We need to choose two distinct approaches that will provide strong security during operation. With that in mind, let's evaluate our options. First, let's look at the options that are incorrect. Option B suggests using IPv6 for security, but the version of the IP protocol doesn't inherently make it more secure. Option D mentions using a functional programming language, which is a software development choice, not a core security architecture principle. Option E, using multiple connectivity systems, is about improving reliability, not security. And Option F, a Faraday cage, protects against electromagnetic interference, which is unrelated to software and network security. This brings us to the correct answers. Let's look at Option C, which is to use a trusted platform module, or TPM, and verify firmware and binaries on boot. This is a critical, foundational security measure. A TPM is a hardware chip that, as part of a secure boot process, cryptographically verifies that the software and firmware loading on the vehicle are authentic and haven't been tampered with by an attacker. The other correct answer is Option A, to treat every microservice call between modules on the vehicle as untrusted. This is the core principle of a zero-trust security model. In a complex system, you assume that an attacker might compromise one small component. By forcing every internal service-to-service call to be authenticated, you prevent an attacker from easily moving around inside the system after their initial breach. Therefore, the two architectural choices you should consider for strong security are A and C. That's all the questions related to Case Study 2. Now let's move on to Case Study 3. Case Study 3. Company Overview. JencoMart is a global retailer with over 10,000 stores in 16 countries. The stores carry a range of goods, such as groceries, tires, and jewelry. One of the company's core values is excellent customer service. In addition, they recently introduced an environmental policy to reduce their carbon output by 50% over the next 5 years. Company background. JencoMart started as a general store in 1931 and has grown into one of the world's leading brands known for great value and customer service. Over time, the company transitioned from only physical stores to a stores and online hybrid model, with 25% of sales online. Currently, JencoMart has little presence in Asia, but considers that market key for future growth. Solution concept. JencoMart wants to migrate several critical applications to the cloud but has not completed a technical review to determine their suitability for the cloud and the engineering required for migration. They currently host all of these applications on infrastructure that is at its end of life and is no longer supported. Existing technical environment. JencoMart hosts all of its applications in 4 data centers, 3 in North America and 1 in Europe. Most applications are dual-homed. JencoMart understands the dependencies and resource usage metrics of their on-premises architecture. Application Customer Loyalty Portal. A LAMP Linux, Apache, MySQL, and PHP application served from the 2 JencoMart-owned U.S. data centers. Database. Oracle Database stores user profiles. 20 terabytes. Complex table structure. Well-maintained, clean data. Strong backup strategy. PostgreSQL database stores user credentials. Single-homed in US West. No redundancy. Backed up every 12 hours. 100% uptime service level agreement. SLA. Authenticates all users. Compute. 30 machines in US West Coast. Each machine has twin dual-core CPUs. 32 gigabytes of RAM. Twin 250 gigabytes HDD. RAID 1. 20 machines in US East Coast. Each machine has single dual-core CPU, 24 gigabytes of RAM, twin 250 gigabytes HDD, RAID 1. Storage. Access to shared 100 terabytes SAN in each location. Tape backup every week. Business requirements. Optimize for capacity during peak periods and value during off-peak periods. Guarantees service availability and support. Reduce on-premises footprint and associated financial and environmental impact. Move to outsourcing model to avoid large upfront costs associated with infrastructure purchase. Expand services into Asia. Technical requirements. Assess key application for cloud suitability. JencoMart case study. Continued from previous images. Modify application for the cloud. Move applications to a new infrastructure. Leverage managed services wherever feasible. Sunset 20% of capacity in existing data centers. Decrease latency in Asia. CEO statement. JencoMart will continue to develop personal relationships with our customers as more people access the web. The future of our retail business is in the global market and the connection between online and in-store experiences. As a large global company, we also have a responsibility to the environment through green initiatives and policies. CTO statement. The challenges of operating data centers prevents focus on key technologies critical to our long-term success. Migrating our data services to a public cloud infrastructure will allow us to focus on big data and machine learning to improve our service customers. CFO statement. Since its founding, JencoMart has invested heavily in our data services infrastructure. However, because of changing market trends, we need to outsource our infrastructure to ensure our long-term success. This model will allow us to respond to increasing customer demand during peak and reduce costs. Question 170. For this question, refer to the JencoMart case study. The JencoMart security team requires that all Google Cloud Platform infrastructure is deployed using a least privilege model with separation of duties for administration between production and development resources. What Google domain and project structure should you recommend? Create 2 G Suite accounts to manage users. 1 for development/test/staging and 1 for production. Each account should contain 1 project for every application. B. Create 2 G Suite accounts to manage users. 1 with a single project for all development applications and 1 with a single project for all production applications. C. Create a single G Suite account to manage users with each stage of each application in its own project. D. Create a single G Suite account to manage users with 1 project for the development/test/staging environment and 1 project for the production environment. Okay, this question from the JencoMart case study is about setting up a proper Google Cloud resource structure. The main goals are security and manageability, specifically making sure there's a clear separation between the development and production environments. With that in mind, let's look at our options. Let's start by looking at options A and B, which both suggest creating two separate G Suite accounts. This is not the recommended practice. It's much simpler and more standard to manage all of your company's users in a single G Suite or Google Workspace account for central administration. Next, option C suggests creating a project for each stage of each application. This is also incorrect because it would lead to a huge number of projects that would become very difficult to manage over time. This brings us to option D, which describes the correct and recommended structure. It provides a good balance between security and manageability. You use a single G Suite account to manage all your users centrally. Then you create one project to hold all of your non-production environments like development, testing, and staging. This allows you to give developers more permissive access in one place. Most importantly, you create a completely separate project for the production environment. This creates a strong security boundary, allowing you to tightly restrict access to the production project, which is the core of a good separation of duties model. Therefore, the project and domain structure you should recommend is D. Create a single G Suite account to manage users with one project for the development/test/staging environment and one project for the production environment. Question 171. For this question, refer to the JencoMart case study. The migration of JencoMart's application to Google Cloud Platform, GCP, is progressing too slowly. The infrastructure is shown in the diagram. You want to maximize throughput. What are three potential bottlenecks? Choose three answers. A single VPN tunnel which limits throughput. B. A tier of Google Cloud storage that is not suited for this task. C. A copy command that is not suited to operate over long distances. D. Fewer virtual machines, VMs, in GCP than on-premises machines. E. A separate storage layer outside the VMs which is not suited for this task. F. Complicated internet connectivity between the on-premises infrastructure and GCP. Okay, this question from the JencoMart case study is a troubleshooting problem. The migration is too slow, and we need to identify three likely reasons or bottlenecks in the described architecture. With that in mind, let's evaluate our options. Let's first look at the incorrect options. Option B is incorrect because the scenario describes data moving to compute engine VMs, not cloud storage, so the storage tier is irrelevant. Option C is unlikely. While an inefficient command can be slow, the major bottlenecks in a large-scale data transfer are almost always in the network infrastructure, not the software command. Option E is also unlikely, as cloud services are designed for high-throughput writes. Now let's look at the correct answers. Option A points to the single VPN tunnel. This is a very likely bottleneck. A single VPN connection has a fixed amount of bandwidth and can easily become saturated when trying to move a large amount of data. Option F, complicated internet connectivity, is another correct answer. The cloud VPN relies on the public internet, and the connection from the on-premise data center to the internet is often a major bottleneck itself due to its own bandwidth limits and complexity. Finally, option D, having fewer virtual machines in GCP, is the third correct answer. If you have many servers on-premise sending data, but only a few VMs on the GCP side to receive it, the receiving end can become overwhelmed and unable to process the incoming data stream fast enough, creating a bottleneck. Therefore, the three most likely bottlenecks are A, D, and F. Question 172. For this question, refer to the JencoMart case study. A few days after JencoMart migrates the user credentials database to Google Cloud Platform and shuts down the old server, the new database server stops responding to SSH connections. It is still serving database requests to the application servers correctly. What three steps should you take to diagnose the problem? Choose three answers. Delete the virtual machine, VM, and disks and create a new one. B. Delete the instance, attach the disk to a new VM, and investigate. C. Take a snapshot of the disk and connect to a new machine to investigate. D. Check inbound firewall rules for the network the machine is connected to. E. Connect the machine to another network with very simple firewall rules and investigate. F. Print the serial console output for the instance for troubleshooting. Activate the interactive console and investigate. Okay, this is a troubleshooting question from the JencoMart case study. The key here is that the database server is in a strange state. The database itself is working, but you can't connect to it with SSH. We need to find 3 safe, non-disruptive ways to diagnose the problem without taking the database offline. With that in mind, let's first look at what not to do. Options A and B are incorrect because they involve deleting the original virtual machine. This is a destructive action, not a diagnostic one, and would erase important evidence needed to find the root cause. Option E is also not a good first step. Changing the network of a live, production database server is a risky and disruptive action that could break the database connectivity that is currently working. Now let's look at the correct diagnostic steps. Option D, checking the inbound firewall rules, is a perfect first step. An inability to SSH is very often caused by a firewall rule that is blocking traffic on port 22. This is a quick and easy check. Option F, using the serial console, is another correct and powerful tool. The serial console gives you low-level access to the VM even if SSH isn't working. It allows you to look at boot messages and system status directly to see if there's an issue with the OS, the network configuration, or an internal firewall. Finally, option C, taking a snapshot of the disk and connecting it to a new machine, is the third correct step. This is a safe way to perform a deep analysis. You can examine the file system and log files on the clone disk without any risk of affecting the original, still running database server. Therefore, the 3 best steps to diagnose the problem are C, D, and F. Question 173. For this question, refer to the JencoMart case study. The JencoMart security team requires that all Google Cloud Platform infrastructure is deployed using a least privilege model with separation of duties for administration between production and development resources. What Google domain and project structure should you recommend? Cloud Spanner. B. Google BigQuery. C. Google Cloud SQL. D. Google Cloud Data Store. Okay, this question from the JencoMart case study asks us to choose the best database for storing user profiles. The key to this is to think about the nature of user profile data. It often has a variety of fields and doesn't require the complex relationships of a traditional relational database, which makes it a great fit for a NoSQL solution. With that in mind, let's look at our options. Let's start with option B, Google BigQuery. This is incorrect because BigQuery is a data warehouse designed for running large analytical queries, not for serving as a live application database for reading and writing individual user profiles. Next, let's look at the relational options, A and C. Cloud Spanner is an incredibly powerful, globally scalable relational database, but it's overly complex and expensive for a simple use case like user profiles. Cloud SQL is a more standard relational database, but its rigid schema can be less flexible than a NoSQL database when it comes to storing user data, which can often change over time. This brings us to option D, which is the correct answer. Google Cloud Data Store, now part of Firestore, is a highly scalable, fully managed NoSQL database. It is specifically designed and recommended for use cases like user profiles, product catalogs, and game states. Its flexible, document-based model is perfect for storing user profile objects that may have different attributes. Therefore, the Google database they should use is D. Google Cloud Data Store. Question 174. For this question, refer to the JencoMart case study. JencoMart has decided to migrate user profile storage to Google Cloud Data Store and the application servers to Google Compute Engine, GCE. During the migration, the existing infrastructure will need access to Data Store to upload the data. What service account key management strategy should you recommend? A. Provision service account keys for the on-premises infrastructure and for the GCE virtual machines, VMs. B. Authenticate the on-premises infrastructure with a user account and provision service account keys for the VMs. C. Provision service account keys for the on-premises infrastructure and use Google Cloud Platform, GCP, managed keys for the VMs. D. Deploy a custom authentication service on GCE/Google Container Engine (GKE) for the on-premises infrastructure and use GCP managed keys for the VMs. Okay, this question from the JencoMart case study is about how to securely authenticate applications in a hybrid environment. We have two different types of systems that need access: the old on-premise infrastructure and the new virtual machines on Google Cloud. The best practice is to use a different, appropriate authentication method for each. With that in mind, let's look at our options. Let's start with option A. This is incorrect because it suggests creating and managing service account key files for the GCE virtual machines. This is not recommended because there's a more secure, automated way to handle authentication for resources running inside Google Cloud. Option B is also incorrect. It suggests using a regular user account for the on-premise infrastructure. Service accounts are designed specifically for applications and automated workloads and should always be used instead of a human user's account. Option D proposes building a custom authentication service. This is overly complex and unnecessary. Google Cloud already provides robust and secure ways to handle this without requiring you to build and maintain your own authentication system. This brings us to option C, which is the correct and recommended solution. It addresses both environments correctly. For the on-premise infrastructure, which is outside Google Cloud, you must provision a downloadable service account key. This is the standard way for an external application to authenticate. For the new virtual machines running on GCE, you use what's called GCP managed keys. This simply means you attach a service account to the VM, and Google automatically handles the credential delivery securely in the background without any key files. This is the most secure and modern approach. Therefore, the correct strategy is C. Provision service account keys for the on-premises infrastructure and use Google Cloud Platform, GCP, managed keys for the VMs. Question 175. For this question, refer to the JencoMart case study. JencoMart has built a version of their application on Google Cloud Platform that serves traffic to Asia. You want to measure success against their business and technical goals. Which metrics should you track? Error rates for requests from Asia. B. Latency difference between US and Asia. C. Total visits, error rates, and latency from Asia. D. Total visits and average latency for users in Asia. E. The number of character sets present in the database. Okay, this question is based on the JencoMart case study and asks us to pick the best metrics to measure the success of their expansion into Asia. The case study gives us two clear goals: a business goal to expand their service, and a technical goal to reduce latency for Asian users. We need to find the metrics that directly track these two goals. With that in mind, let's look at our options. Let's look at the options that are incomplete. Option A, just tracking error rates, is not enough because it doesn't tell us if they are attracting any users or if the performance is good. Option B, which only compares latency between the US and Asia, is also incomplete as it ignores the business goal of user adoption. Option E is incorrect because the number of character sets in a database is an implementation detail, not a key metric for measuring business success or user experience. Option C is close, but latency is a very general term. A more precise and standard metric for user experience is average latency. This brings us to option D, which is the correct answer. It perfectly aligns with the two main goals from the case study. Total visits is the key business metric that directly measures the success of the expansion into Asia. Average latency is the key technical metric that directly measures whether they have successfully reduced latency for those users. This pair of metrics gives a complete picture of both business and technical success. Therefore, the metrics you should track are D, total visits, and average latency for users in Asia. That's all the questions related to case study 3. Now let's move on to case study 4. Case study, Dress4Win. Company overview. Dress4Win is a web-based company that helps their users organize and manage their personal wardrobe using a website and mobile application. The company also cultivates an active social network that connects their users with designers and retailers. They monetize their services through advertising, e-commerce, referrals, and a freemium app model. Company background. Dress4Win's application has grown from a few servers in the founder's garage to several hundred servers and appliances in a co-locate data center. However, the capacity of their infrastructure is now insufficient for the application's rapid growth. Because of this growth and the company's desire to innovate faster, Dress4Win is committing to a full migration to a public cloud. Solution concept. For the first phase of their migration to the cloud, Dress4Win is considering moving their development and test environments. They are also considering building a disaster recovery site because their current infrastructure is at a single location. They are not sure which components of their architecture they can migrate as is and which components they need to change before migrating them. Existing technical environment. The Dress4Win application is served out of a single data center location. Databases. MySQL user data inventory static data. Redis metadata social graph. Caching. Application servers. Tomcat Java microservices. Nginx static content. Apache Beam batch processing. Storage appliances. ISCSI for VM hosts. Fiber channel SAN MySQL databases. NAS image storage, logs, backups. Apache Hadoop/Spark servers. Data analysis. Real-time trending calculations. MQ servers. Messaging. Social notifications. Events. Miscellaneous servers. Jenkins monitoring Bastion host security scanners. Business requirements. Build a reliable and reproducible environment with scaled parity of production. Improve security by defining and adhering to a set of security and identity and access management (IAM) best practices for cloud. Improve business agility and speed of innovation through rapid provisioning of new resources. Analyze and optimize architecture for performance in the cloud. Migrate fully to the cloud if all other requirements are met. Technical requirements. Evaluate and choose an automation framework for provisioning resources in cloud. Support failover of the production environment to cloud during an emergency. Identify production services that can migrate to cloud to save capacity. Use managed services whenever possible. Encrypt data on the wire and at rest. Support multiple VPN connections between the production data center and cloud environment. CEO statement. Our investors are concerned about our ability to scale and contain costs with our current infrastructure. They are also concerned that a new competitor could use a public cloud platform to offset their upfront investment and freeing them to focus on developing better features. CTO statement. We have invested heavily in the current infrastructure, but much of the equipment is approaching the end of its useful life. We are consistently waiting weeks for new gear to be racked before we can start new projects. Our traffic patterns are highest in the mornings and weekend evenings. During other times, 80% of our capacity is sitting idle. CFO statement. Our capital expenditure is now exceeding our quarterly projections. Migrating to the cloud will likely cause an initial increase in spending, but we expect to fully transition before our next hardware refresh cycle. Our total cost of ownership, TCO, analysis over the next 5 years puts a cloud strategy between 30 to 50% lower than our current model. Question 176. For this question, refer to the Dress4Win case study. At Dress4Win, an operations engineer wants to create a low-cost solution to remotely archive copies of database backup files. The database files are compressed tar files stored in their current data center. How should he proceed? A. Create a cron script using sutil to copy the files to a cold line storage bucket. B. Create a cron script using sutil to copy the files to a regional storage bucket. C. Create a cloud storage transfer service job to copy the files to a cold line storage bucket. D. Create a cloud storage transfer service job to copy the files to a regional storage bucket. Okay, this question from the Dress4Win case study is about finding the most cost-effective and automated way to archive on-premises backups to Google Cloud. To solve this, we need to choose the right tool for the transfer and the right storage class for the archival. With that in mind, let's look at our options. First, let's consider the storage class. The goal is a low-cost solution for archiving backups, which are rarely accessed. Cold line storage is the cheapest storage class designed for this exact purpose. Regional storage is more expensive and meant for data that is accessed more frequently. Therefore, we can eliminate options B and D because they use the less cost-effective regional storage. Now we are left with options A and C, which both correctly use cold line storage. The difference is the tool used for the transfer. Option C suggests using the Cloud Storage Transfer Service. This service is typically used for large-scale migrations from other cloud providers or between cloud storage buckets. For an ongoing, scheduled task of copying files from an on-premise server, the simpler and more standard tool is certpro. This brings us to option A, which is the correct solution. It combines the right tool with the right storage class. You would create a cron script on your on-premise server that uses the certpro command line tool to copy the backup files. This script would upload the files to a cold line storage bucket, which provides the lowest storage cost for archival. This approach is automated, uses the standard tool for the job, and is the most cost-effective. Therefore, the way he should proceed is create a cron script using certpro to copy the files to a cold line storage bucket. Question 177. For this question, refer to the Dress4Win case study. Dress4Win has asked you to recommend machine types they should deploy their application servers to. How should you proceed? A. Perform a mapping of the on-premises physical hardware cores and RAM to the nearest machine types in the cloud. B. Recommend that Dress4Win deploy application servers to machine types that offer the highest RAM to CPU ratio available. C. Recommend that Dress4Win deploy into production with the smallest instances available, monitor them over time, and scale the machine type up until the desired performance is reached. D. Identify the number of virtual cores and RAM associated with the application server virtual machines, align them to a custom machine type in the cloud, monitor performance, and scale the machine types up until the desired performance is reached. Okay, this question from the Dress4Win case study is about how to choose the right size for your virtual machines on Google Cloud. The goal is to find a process that gives you the performance you need without wasting money on oversized servers. With that in mind, let's look at our options. Let's start with option A, which suggests mapping from your on-premises physical hardware. This is not a good practice because it often leads to over-provisioning and spending too much money. Cloud instances are often more efficient than older physical hardware. Option B is also incorrect. Choosing the machine type with the highest RAM to CPU ratio without knowing if your application actually needs that much memory is a recipe for wasting resources. Next, let's look at option D. This is better than mapping from physical hardware, but mapping from your old on-premise virtual machines still carries the risk of over-provisioning. The best way is to validate your actual needs on the cloud platform itself. This brings us to option C, which describes the correct and most cost-effective approach. This is often called right-sizing. You start by deploying your application on small, inexpensive instances. Then, you monitor their performance under a real workload. Based on that data, you can gradually scale up the machine type until you find the perfect balance of performance and cost. This ensures you only pay for the resources your application actually uses. Therefore, the way you should proceed is C. Recommend that Dress4Win deploy into production with the smallest instances available, monitor them over time, and scale the machine type up until the desired performance is reached. Question 178. For this question, refer to the Dress4Win case study. Dress4Win has asked you for advice on how to migrate their on-premises MySQL deployment to the cloud. They want to minimize downtime and performance impact to their on-premises solution during the migration. Which approach should you recommend? Create a dump of the on-premises MySQL master server, and then shut it down, upload it to the cloud environment, and load into a new MySQL cluster. B. Set up a MySQL replica server/slave in the cloud environment, and configure it for asynchronous replication from the MySQL master server on-premises until cutover. C. Create a new MySQL cluster in the cloud, configure applications to begin writing to both on-premises and cloud MySQL masters, and destroy the original cluster at cutover. D. Create a dump of the MySQL replica server into the cloud environment, load it into Google Cloud Data Store, and configure applications to read/write to Cloud Data Store at cutover. Okay, this question from the Dress4Win case study is about migrating a live MySQL database to the cloud. The most important requirements are to do this with minimal downtime and without slowing down the current on-premises system during the process. With that in mind, let's look at our options. Let's start with option A. It suggests creating a dump of the database and then shutting it down. This is incorrect because shutting down the master database would cause a long period of downtime, which directly violates the main requirement. Next, let's look at option C, which suggests configuring the application to write to both the old and new databases at the same time. This is also not a good approach. A dual write setup is very complex to implement and can easily lead to data consistency problems. Option D is incorrect because it suggests migrating the data to Google Cloud Data Store. This would be a move from a relational database to a NoSQL database, which is a major and complex re-architecture project, not a simple migration. This brings us to option B, which describes the correct and standard industry practice for this type of migration. You set up a new MySQL server in the cloud and configure it as a replica or slave of your on-premises master database. You then use asynchronous replication to continuously copy all the changes from the on-premises database to the cloud replica. This has very little performance impact on your live system. When you are ready to switch over, the only downtime required is a very brief window to stop the application. Make sure the last few changes have been replicated, and then repo-int your application to the new database in the cloud. Therefore, the approach you should recommend is B. Set up a MySQL replica server/slave in the cloud environment, and configure it for asynchronous replication from the MySQL master server on-premises until cutover. Question 179. For this question, refer to the Dress4Win case study. Dress4Win has configured a new uptime check with Google Stackdriver for several of their legacy services. The Stackdriver dashboard is not reporting the services as healthy. What should they do? A. Install the Stackdriver agent on all of the legacy web servers. B. In the Cloud Platform console, download the list of the uptime servers' IP addresses and create an inbound firewall rule. C. Configure their load balancer to pass through the user agent HTTP header when the value matches Google Stackdriver monitoring uptime checks. D. Configure their legacy web servers to allow requests that contain the user agent HTTP header when the value matches Google Stackdriver monitoring uptime checks. Okay, this is a troubleshooting question from the Dress4Win case study. The problem is that a newly configured uptime check is failing, even though the service might be running. An uptime check works by having Google servers around the world try to connect to your application's public address. If they can't connect, the check fails. The most common reason they can't connect is because a firewall is blocking their request. With that in mind, let's look at our options. Let's start with option A, installing the Stackdriver agent. This is incorrect. The agent is for collecting metrics from inside your server. An uptime check is an external test and doesn't require an agent. Next, options C and D suggest configuring rules based on the user agent header. While it's true that the uptime checker uses a specific header, this is not the primary or most reliable way to solve the problem. The most common issue is a network firewall blocking the connection based on its source IP address. This brings us to option B, which is the correct and standard solution. Google's uptime checkers send requests from a well-defined, public list of IP addresses. The most common reason for a check to fail is that your firewall is blocking traffic from these IPs. To fix this, you need to find that official list of Google's uptime server IPs and create an inbound firewall rule that allows traffic from those sources to reach your application. Therefore, the correct thing to do is B. In the Cloud Platform console, download the list of the uptime server's IP addresses and create an inbound firewall rule. Question 180. For this question, refer to the Dress4Win case study. You want to ensure Dress4Win sales and tax records remain available for infrequent viewing by auditors for at least 10 years. Cost optimization is your top priority. Which cloud services should you choose? Google Cloud Storage Cold Line to store the data and SQL to access the data. B. Google Cloud Storage Nearline to store the data and SQL to access the data. C. Google Bigtable with US or EU as location to store the data and cloud to access the data. D. BigQuery to store the data and a web server cluster in a managed instance group to access the data. Google Cloud SQL mirrored across two distinct regions to store the data, and a Redis cluster in a managed instance group to access the data. Okay, this question from the Dress4Win case study is about choosing the right storage solution for long-term data archival. The most important requirements are that the data will be viewed very infrequently and that cost optimization is the top priority. With that in mind, let's evaluate our options. Let's start by looking at the options that suggest using a database, which are C and D. Both Bigtable and BigQuery are powerful data services, but they are designed for high-performance or analytical workloads, not for low-cost, long-term archival. They would be far too expensive for this use case. This leaves us with options A and B, which both correctly identify Google Cloud Storage as the right service. The only difference is the storage class, cold line versus nearline. Option B suggests using nearline storage. Nearline is designed for data you access infrequently, about once a month. However, option A suggests cold line storage. Cold line is designed for true archival data that you expect to access less than once a year. Since the data is for auditors and needs to be kept for 10 years, the access frequency will be very low. Cold line offers the lowest monthly storage cost, making it the most cost-effective choice and the correct answer. Both options correctly mention using sutil, the standard command line tool, to access the data when needed. Therefore, the best choice to meet the cost optimization priority is a Google Cloud Storage cold line to store the data and sutil to access the data. Question 181. For this question, refer to the Dress4Win case study. Dress4Win has end-to-end tests covering 100% of their endpoints. They want to ensure that the move to the cloud does not introduce any new bugs. Which additional testing methods should the developers employ to prevent an outage? A. They should enable Google Stackdriver Debugger on the application code to show errors in the code. B. They should add additional unit tests and production scale load tests on their cloud staging environment. C. They should run the end-to-end tests in the cloud staging environment to determine if the code is working as intended. D. They should add canary tests so developers can measure how much of an impact the new release causes to latency. Okay, this question from the Dress4Win case study is about building a comprehensive testing strategy. They already have good end-to-end tests, but the key here is to find what additional testing methods are needed to make sure their move to the cloud is successful and doesn't cause any outages. With that in mind, let's look at our options. Let's start with option A, which suggests using Stackdriver Debugger. This is incorrect because the debugger is a tool you use to investigate problems in a live, running application. It's not a testing method you use to prevent bugs from getting to production in the first place. Next, option C suggests running their existing end-to-end tests in the new cloud environment. While this is absolutely something they must do, it doesn't count as an additional testing method. The question asks what else they should add. Option D suggests adding canary tests. This is also incorrect in this context. A canary test is a deployment strategy used in production, not a testing method used in a pre-production staging environment. It's one of the last steps in a release process, not an earlier testing phase. This brings us to option B, which is the correct answer. It adds two critical types of testing that are missing. First, additional unit tests are essential for checking the correctness of individual pieces of code at a granular level, which end-to-end tests don't do. Second, production scale load tests are vital for a cloud migration. They are the only way to be confident that the new cloud infrastructure can handle the same amount of traffic as the old system without performance issues or crashing. Therefore, the additional testing methods the developers should employ are B. They should add additional unit tests and production scale load tests on their cloud staging environment. Question 182. For this question, refer to the Dress4Win case study. As part of their new application experience, Dress4Win allows customers to upload images of themselves. The customer has exclusive control over who may view these images. Customers should be able to upload images with minimal latency and also be shown their images quickly on the main application page when they log in. Which configuration should Dress4Win use? Store image files in a Google Cloud Storage bucket. Use Google Cloud Data Store to maintain metadata that maps each customer's ID and their image files. B. Store image files in a Google Cloud Storage bucket. Add custom metadata to the uploaded images in cloud storage that contains the customer's unique ID. C. Use a distributed file system to store customers' images. As storage needs increase, add more persistent disks and/or nodes. Assign each customer a unique ID, which sets each file's owner attribute, ensuring privacy of images. D. Use a distributed file system to store customers' images. As storage needs increase, add more persistent disks and/or nodes. Use a Google Cloud SQL database to maintain metadata that maps each customer's ID to their image files. Okay, this question from the Dress for Win case study is about designing the best architecture for storing user-uploaded images. The key requirements are that it must be fast for both uploads and downloads, and there needs to be a secure way to manage which images belong to which user. With that in mind, let's look at our options. Let's first look at the options that suggest using a distributed file system, which are C and D. These are incorrect because building and managing your own file system on top of virtual machines and persistent disks is a very complex and operationally intensive task. It's much better to use Google's fully managed storage services. Next, let's look at option B. It correctly suggests storing the image files in a cloud storage bucket, but it recommends using the object's custom metadata to store the customer's ID. This is not an efficient solution. Querying for all objects with a specific metadata tag is very slow compared to looking up data in a purpose-built database. This brings us to option A, which describes the correct and standard architecture for this use case. This pattern separates the storage of the large image files from the storage of their metadata. You store the actual image files in a Google Cloud storage bucket, which is infinitely scalable and highly performant for this purpose. Then you use a fast, scalable NoSQL database like Cloud Data Store to store the metadata, which is simply a map of each customer's ID to the list of their image files. This allows your application to very quickly query the database to find the images for a specific user and then display them. Therefore, the configuration Dress for Win should use is a store image files in a Google Cloud storage bucket and use Google Cloud Data Store to maintain metadata that maps each customer's ID and their image files. Question 183. For this question, refer to the Dress for Win case study. The Dress for Win security team has disabled external SSH access into production virtual machines, VMs, on Google Cloud Platform, GCP. The operations team needs to remotely manage the VMs, build and push Docker containers, and manage Google Cloud storage objects. What can they do? A. Grant the operations engineers access to use Google Cloud Shell. B. Configure a VPN connection to GCP to allow SSH access to the cloud VMs. C. Develop a new access request process that grants temporary SSH access to cloud VMs when an operations engineer needs to perform a task. D. Have the development team build an API service that allows the operations team to execute specific remote procedure calls to accomplish their tasks. Okay, this question from the Dress for Win case study is about finding a secure way for an operations team to manage cloud resources when direct external SSH access has been disabled for security reasons. We need a solution that is secure, easy to use, and doesn't require a lot of complex setup. With that in mind, let's look at our options. Let's start by looking at the options that involve significant effort. Option B, configuring a VPN, is a valid but complex and costly solution. Option C, developing a new access request process, adds manual overhead. And option D, building a custom API, is an enormous engineering task. All of these are much more complicated than necessary. This brings us to option A, which is the correct and Google-recommended solution. Google Cloud Shell is a managed, browser-based command line environment that runs within Google Cloud. It comes pre-installed with all the tools the operations team needs, like Cloud, SUDL, and Docker. The operations team can access this secure environment from anywhere. Because Cloud Shell is inside Google's network, when they SSH from it to a production VM, it's considered internal traffic, so it doesn't violate the no external SSH policy. This is the simplest, most secure, and lowest overhead solution to the problem. Therefore, the best thing they can do is grant the operations engineers access to use Google Cloud Shell. Question 184. For this question, refer to the Dress4Win case study. Dress4Win would like to become familiar with deploying applications to the cloud by successfully deploying some applications quickly. As is, they have asked for your recommendation. What should you advise? Identify self-contained applications with external dependencies as a first move to the cloud. B. Identify enterprise applications with internal dependencies and recommend these as a first move to the cloud. C. Suggest moving their in-house databases to the cloud and continue serving requests to on-premise applications. D. Recommend moving their message queuing servers to the cloud and continue handling requests to on-premise applications. Okay, this question from the Dress4Win case study is about migration strategy. The goal is to find the best type of application to move to the cloud first, to ensure a quick and successful initial deployment that builds confidence. With that in mind, let's look at our options. Let's first look at options C and D, which suggest moving core backend components like databases or message queues first, while leaving the application on premises. This is not a good first step. It creates a split architecture that can introduce significant network latency between the application and its data, leading to major performance problems. Next, let's look at option B. It suggests moving enterprise applications with many internal dependencies. This is also a bad idea for a first move. These are typically the most complex and risky applications to migrate, which is the opposite of the quick and successful goal. This brings us to option A, which is the correct advice. The best candidates for a first migration are self-contained applications that have few, if any, dependencies on other internal on-premise systems. Because they are self-contained, they are the easiest and least risky to move. Successfully migrating these applications provides a valuable quick win and allows the team to gain experience and confidence with the cloud before tackling more complex workloads. Therefore, the advice you should give is identify self-contained applications with external dependencies as a first move to the cloud. Question 185. For this question, refer to the Dress4Win case study. As part of Dress4Win's plans to migrate to the cloud, they want to be able to set up a managed logging and monitoring system so they can handle spikes in their traffic load. They want to ensure that the infrastructure can be notified when it needs to scale up and down to handle the ebb and flow of usage throughout the day. Their administrators are notified automatically when their application reports errors. They can filter their aggregated logs down in order to debug one piece of the application across many hosts. Which Google Stackdriver features should they use? Logging, alerts, insights, debug. B. Monitoring, trace, debug, logging. C. Monitoring, logging, alerts, error reporting. D. Monitoring, logging, debug, error report. Okay, this question from the Dress4Win case study asks us to pick the right set of tools from the Google Cloud's Operations Suite, formerly known as Stackdriver, to meet three specific needs: triggering auto-scaling, alerting on errors, and debugging with logs. With that in mind, let's look at our options. Let's start with option A. This is incorrect because it's missing monitoring. The monitoring service is what collects the performance metrics, like CPU utilization, that are needed to inform the infrastructure when it's time to scale up or down. Next, let's look at option B. This option is incorrect because it's missing alerts and error reporting. These are the specific features used to automatically notify administrators when application errors occur, which is a key requirement of the question. Option D is also incorrect. It includes the debugger service instead of alerts. The debugger is a tool for inspecting the state of live code, not for sending automated notifications to the operations team. This brings us to option C, which is the correct answer. This set of features perfectly matches all the requirements. Monitoring is used to collect the metrics needed for auto-scaling. Logging is used to collect and filter the aggregated logs for debugging. And alerts, often working with error reporting to group application errors, is the tool used to automatically notify administrators when problems occur. Therefore, the Stackdriver features they should use are C, monitoring, logging, alerts, and error reporting. Question 186. For this question, refer to the Dress4Win case study. Dress4Win has end-to-end tests covering 100% of their endpoints. They want to ensure that the move of cloud does not introduce any new bugs. Which additional testing methods should the developers employ to prevent an outage? They should run the end-to-end tests in the cloud staging environment to determine if the code is working as intended. B. They should enable Google Stackdriver Debugger on the application code to show errors in the code. C. They should add additional unit tests and production scale load tests on their cloud staging environment. D. They should add canary tests so developers can measure how much of an impact the new release causes to latency. Okay, this question from the Dress for Win case study is about building a comprehensive testing strategy. They already have good end-to-end tests, but the key here is to find what additional testing methods are needed to make sure their move to the cloud is successful and doesn't cause any outages. With that in mind, let's look at our options. Let's start with option A, which suggests running their existing end-to-end tests in the new cloud environment. While this is absolutely something they must do, it doesn't count as an additional testing method. The question asks what else they should add. Next, option B suggests using Stackdriver Debugger. This is incorrect because the debugger is a tool you use to investigate problems in a live, running application. It's not a testing method you use to prevent bugs from getting to production in the first place. Option D suggests adding canary tests. This is also incorrect in this context. A canary test is a deployment strategy used in production, not a testing method used in a pre-production staging environment. It's one of the last steps in a release process, not an earlier testing phase. This brings us to option C, which is the correct answer. It adds two critical types of testing that are missing. First, additional unit tests are essential for checking the correctness of individual pieces of code at a granular level, which end-to-end tests don't do. Second, production scale load tests are vital for a cloud migration. They are the only way to be confident that the new cloud infrastructure can handle the same amount of traffic as the old system without performance issues or crashing. Therefore, the additional testing methods the developers should employ are C. They should add additional unit tests and production scale load tests on their cloud staging environment. Question 187. For this question, refer to the Dress for Win case study. The current Dress for Win system architecture has high latency to some customers because it is located in one data center. As of a future evaluation and optimizing for performance in the cloud, Dress for Win wants to distribute its system architecture to multiple locations on Google Cloud Platform. Which approach should they use? Use regional managed instance groups and a global load balancer to increase performance because the regional managed instance group can grow instances in each region separately based on traffic. B. Use a global load balancer with a set of virtual machines that forward the requests to a closer group of virtual machines managed by your operations team. C. Use regional managed instance groups and a global load balancer to increase reliability by providing automatic failover between zones in different regions. D. Use a global load balancer with a set of virtual machines that forward the requests to a closer group of virtual machines as part of a separate managed instance groups. Okay, this question from the Dress for Win case study is about solving a classic performance problem: high latency for a global user base. The root of the issue is that their application is in a single data center, so users who are far away experience a slow response. The goal is to design an architecture that brings the application closer to all users. With that in mind, let's evaluate our options. Let's start by looking at options B and D. Both of these suggest a complex architecture where you have one set of virtual machines that just forwards requests to another set. This is incorrect because it's an unnecessary and inefficient design. A global load balancer is already intelligent enough to send traffic directly to the closest backend servers. Next, let's look at option C. This option describes the correct architecture using a global load balancer and regional managed instance groups, but it gives the wrong primary reason. While this setup does improve reliability, the main goal stated in the question is to optimize for performance and reduce latency. This brings us to option A, which is the correct answer. It proposes the standard and best practice architecture for a global application. You use a global load balancer, which provides a single IP address for all users and automatically routes them to the Google Cloud region that is geographically closest to them. Then, in each of those regions, you have a regional managed instance group running your application. This setup ensures that users are always served by the servers nearest to them, which dramatically reduces latency. It also allows each region's instance group to scale independently based on its local traffic, which is very efficient. Therefore, the approach they should use is use regional managed instance groups and a global load balancer to increase performance because the regional managed instance group can grow instances in each region separately based on traffic.